Hello dear students, welcome you all to Maverick Physics classes. Today I start first harmonic oscillation. In our last video I had discussed about fault oscillation without damping, and we have seen that the two solutions, one is complementary solution, other one is particular integral solutions, are nothing but in the form of our solution of simple harmonic motion. That means forced oscillation without damping is nothing but a linear combination of two simple harmonic motions which are oscillating about mean position x equal to 0. These things I had discussed in my last video. So today we start from here. Today we have to proceed for forced damped oscillation, or simply I am writing forced harmonic oscillation. Okay, and also I had discussed about forced oscillation. What is our forced oscillation? We have seen that in damped harmonic oscillation, the amplitude of oscillation decreases continuously due to dissipative force or resistive force exist in the medium, and our energy loss occurs there, and this loss of energy is seen in the form of heat, which may be not in very big amount you can realize, but it happens. The loss in energy due to damping is converted into heat. Okay. Now if you want to maintain the oscillation, you have to apply continuous periodic force so that our oscillation will be maintained. Okay. So if I write the equation for our forced harmonic oscillation, it will be like this. Net force on our oscillator is F net. I am not writing it in vector form, writing in simple manner, because in last videos I had already written these equations in vector form. You can go for that if any doubt arises. You can go for my playlist and search the video there. Watch the video, then come here. So net force is our restoring force plus damping force, then our external periodic force. Okay, it's very easy. If you want to write it in vector form, nothing to worry. Put arrows here, then you write the equation. F net is our F net along which direction? Along positive x-axis. You can take the example of spring mass system. Okay, net force is along this direction. Restoring force is along this direction, minus I cap direction. Damping force is also against our motion, that means it is also in minus I direction. Our external periodic force is to counter this damping force, against this damping force, along the positive x direction. So this vector equation becomes like this: F net I cap, then you go for FR and minus I cap, then you go for FD, also minus I cap, then our plus F external I cap. Very easy to write this equation. The I cap is the unit vector along positive x direction. So this equation now of the form F net is equal to minus FR, then minus FD, then plus F external. Here, this is the net force on our oscillator of mass M, subject to this restoring force FR, damping force FD, and external periodic force F external. What will be the net force? According to Newton's second law, it is M in mass times acceleration, and we can write it like this: M d square x upon dt square is equal to, minus sign is here. We are writing only magnitude. FR is minus kx, but that is in vector form. If you write FR vector is equal to minus k into x vector, if you take magnitude of this, it will be plus kx. So don't get confused. This is our magnitude, because when we write a vector in component form, it is our magnitude associated with unit vector. This is our magnitude. That means kx only, not minus kx. Okay. Then minus sign is here. FD magnitude is bv. then plus F external. This external periodic force is of the, it should be periodic function. This force should be expressed in periodic manner with the help of a periodic function, and we have already sinusoidal functions for our oscillation. So I can write it small f cos then omega t minus delta, like this. I am writing it like this. Our external periodic force, let it be fast like this, then we proceed further. F cos omega t. Delta is the phase, we will discuss it later. Equation is of the form like this. Net force is m d square x upon d square. Negative sign is here. Fr magnitude is x. Negative sign is here. Fd magnitude is bv. Then our external periodic force, as I had already told you in my last video, in forced oscillation without damping, it is simply F. F is the amplitude of driven force, and cos omega t. Omega is our angular frequency of driving force. Okay. Then just rearrange. What will I do? D square x upon dt square, that means dividing m, then plus b by m into v, then plus k by m into x is equal to our f by m into cos omega t. Okay. And you know, already I have written this value. B by m is our 2 beta, k by m is our omega naught square, f by m force upon mass is our acceleration. So everything you know. I can write now d square x upon dt square plus b by m is our 2 beta, v velocity, we can write it dx upon dt, okay, plus k by m is our omega naught square, x is equal to f by m, this is our acceleration small f, and cos omega t. So this is this is the differential equation of motion of our post harmonic oscillator. Okay, this is the differential equation. What are the symbols used here? Let me write it again, although I have written it. Beta, where the symbol beta is b by 2m, which is our damping coefficient. You already know this. If you don't know, you can go for my playlist and watch the video there. Damping coefficient beta is equal to b by 2m. And omega naught is square root of k by m. This is our omega naught is our natural frequency of the oscillator. Okay, this is the differential equation of forced harmonic oscillation. And just go for this differential equation. This is a second order, you can find its degree and order. Second order differential equation. Second order inhomogeneous, RHS is not 0 here. Second order inhomogeneous linear differential equation with constant coefficients beta omega naught like this, 2 beta omega naught. Okay, so this is the equation. This is a, I write it here. You may make note. So this equation is a second order differential equation. Second order inhomogeneous linear differential equation with constant coefficients. Okay. Now, what is our aim? Our aim is to solve this differential equation and get a solution, then analyze this solution to get information, everything about our forced harmonic oscillator. We go for that. Let's find the solution of this differential equation. Don't forget this differential equation. I repeat, d square x upon dt square plus 2 beta dx upon dt plus omega naught square x is equal to small f cos omega t. This is our differential equation. As you know, this is the inhomogeneous differential equation. So its solution, general solution of this equation is of the form as previously I had written. The general solution is of the form, right, like this, is of the form x is equal to xct plus xpt. xct plus xpt. xct is our complementary solution and xpt is our particular integral solution. Okay, I had already discussed about all these things in first oscillation without damping. You can go for that. And from there, I had told you in my last video that the complementary solution can be obtained by simply putting the RHS of differential equation to 0. Our differential equation is, I am writing here again, d square x upon dt square plus 2 beta dx upon dt plus omega naught square x is equal to small f cos omega t. This is our differential equation. This xct, complementary solution, can be obtained by putting this RHS to 0. And if you put the RHS to 0, this equation becomes d square x upon dt square plus 2 beta dx by dt plus omega naught square x is equal to 0. You better know this equation. This is our differential equation for damped harmonic oscillation. And we have already got its solution. And its solution is, if you remember that, I am writing here xct, it is e to the power minus beta t, okay, then some constant c1 e to the power square root beta square minus omega naught square into t plus some constant c2 e to the power negative beta square minus omega naught square into t. And this is the solution. If you don't know this, no, not worry, go for the playlist and this video is already available. You watch damped harmonic oscillation. I have set up this differential equation there and then obtained this solution. Okay, you can watch this video in our playlist. This is the solution. If I put RHS to 0, this equation becomes differential equation of damped harmonic oscillation. And we have already obtained its solution xct is equal to this much. So no need to find it again. Simply I have write it here. This is our complementary solution. And for particular integral solution, we can proceed as before. Let the particular integral solution is of the form xpt is equal to, as I have already done there, we may take xpt is equal to a, okay, cos omega t minus delta. Why I have chosen like this solution? No doubt it's a periodic function, solution will be sinusoidal wave. Better I have to choose it first. Delta is our phase of the oscillation. You may go for the physical situation where this fault harmonic oscillation can be realized. If you are riding a bicycle and when wind is blowing and wind is opposing your motion of your bicycle, then what will you do? You simply stand up and do paddling to counter this damping force by our wind. And at the very instant you are standing and paddling, damping force cannot be countered. It will take some time to act your external force. That means you have applied. That means when you stand up and you do paddling more and more rapidly, this force will act on your bicycle after some time. This time interval is your delta. Okay. So this is our phase. You may get it like this. Now we have to find the solution. Find the value of this A and delta. This solution is not clear. We have assumed the solution in such a form. Now differentiate this dx upon dt. D find its derivative. It is minus A omega sin omega t minus delta. Again differentiate t square x pt upon dt square. This is minus A is here. Another omega will come. So it is omega square cos omega t minus delta. Put all these values in this equation, differential equation for harmonic oscillation. So if you put this value here, it is minus A omega square. Let me make some space and write it clearly. Okay? Write it clearly. So I write minus A omega square, then cos omega t minus delta. This is d square x upon dt square plus 2 beta dx upon dt. Dx upon dt is also negative. So I write minus 2 beta and dx upon dt is A omega sin omega t minus delta. Then plus omega naught square x plus omega naught square into x. X is our A cos x means xpt. A cos omega t minus delta is equal to f cos omega t. F cos omega t, we can write it f cos omega t minus delta plus delta. Write it like this. F cos omega t can be written like this. Sorry, f cos omega t minus delta plus delta. It is cos A plus B, and you can write it cos A, that means cos omega t minus delta, cos B, simply cos delta minus sin A, sin omega t minus delta, and sin B, simply sin delta. Okay? This is the differential equation form. Okay? After putting our these values. So now as we have put equal sign, let's equate the coefficients of this cos omega t minus delta and sin omega t minus delta from both sides. As you have put equal sign here, that means the coefficient of cos omega t minus delta from both sides must be equal, and separately the coefficient of sin omega t minus delta are also equal. Okay, so first equating the coefficient of cos omega t minus delta and sin omega t minus delta from both sides. Equate. First go for cos omega t minus delta. If you equate, it is minus A omega square and it is plus omega naught square A is equal to, this is your small f cos delta. Small f cos delta. Okay? Arrange it. You can write it like this: A omega naught square minus omega square is equal to f cos delta. This is our one equation. And if you go for sin omega t minus delta, that means equating the coefficient of sin omega t minus delta from both sides. Here the coefficient is minus 2 beta A omega, and here the coefficient is minus f sin delta. So I am writing equating minus 2 beta A omega is equal to minus f sin delta. This minus minus becomes plus, and 2 beta a omega is equal to f sin delta. Okay. Suppose we have written so many equations, we have to put equation numbers from the beginning. Okay. I had already left them, so let's start it. Here is equation 1, here is equation 2. Now you square and add. What is your m? Our m is to find the value of a and delta. A is our amplitude of oscillation and delta is the phase of oscillation. These two parameters we are going to find. Okay. So for that, let us add square and add simultaneously. If you square this, it will be f square sin square delta. If you square this, it is f square plus square delta. Then add. So write f square sin square delta. Adding, squaring and adding. Right. Squaring and adding. It will be f square sin square delta plus f square plus square delta is equal to, if you square this, it is 4 beta square s square omega square, and this is plus s square omega naught square minus omega square whole square. Squaring and adding. Squaring and adding like this. Then it will be taking f square common, sin square delta plus cos square delta is 1. No need to write it again. So it is 4 beta square omega square plus omega naught square minus omega square whole square. This much into a square taking common. This much into a square taking common. This is our f square. Is it not visible? So I am writing it again. Yes, not visible. Perhaps not visible. Writing it again. So our f square is f square. Sin square delta plus cos square delta, f square taking common is 1. So the f square is equal to 4 beta square s square omega square, s square taking common, 4 beta square omega square plus omega naught square minus omega square whole square. This much into s square. Okay. Then our s square will be small f square upon 4 beta square omega square plus omega naught square minus omega square whole square. This is our s square, and if you go for a, it will be square root. Square root of f is this, and this is square root of this much. This is our amplitude of harmonic oscillation. Our next target is delta, phase of the oscillation. For that, you can simply divide equation 1 and 2. If you divide equation 1 and 2, here is f sin delta, here is f cos delta. Divide f sin delta by f cos delta, sin delta by cos delta, it is tan delta. Okay, f cancel. Tan delta is equal to, here is 2 beta a omega upon a into omega naught square minus omega square. Okay, this is our tan delta. Or you simply may cancel a. Our delta will be tan inverse 2 beta omega upon omega naught square minus omega square. This is our delta. So, two things are important here from all these calculations. One is our amplitude of oscillation, second one is our phase of oscillation. Okay? I think you people must have written all these things. Let me erase all these things, let me make some space so that I write the solution. What will be the solution of our differential equation, complementary solution? xpt, we have assumed a cos omega t minus delta. This is our complementary solution, sorry, particular integral solution. And in place of a, I write this small f upon square root 4 beta square omega square plus omega naught square minus omega square whole square. This is our xpt. This is the value of a. Then cos omega t minus delta. Delta is your tan inverse 2 beta omega upon omega naught square minus omega square. This is our particular integral solution. Okay. So what will be the general solution? General solution x is equal to linear combination of these two solutions, complementary solution and particular integral solutions. I had already written the complementary solution. Xct our e to the power minus beta t, then c1 e to the power square root beta square minus omega naught square into t plus c2 e to the power minus square root beta square minus omega naught square into t, and our particular integral solution is this much. Okay, but this complementary solution, this one is a transient solution. What do you mean? Transient means this solution exists for very small time. Why? Once your external periodic force acts on the oscillator, the dominance of damping in the medium gets slowly vanishes and finally zero. As far as damping is concerned, or up to the time damping is there in our medium, this solution exists. Once damping vanishes due to predominance of our external periodic force, this solution also vanishes. So this is a transient solution. Our final solution will be x is equal to simply xpt, that means this much. F by square root per beta square omega square plus omega naught square minus omega square whole square cos omega t minus this. So this is our final solution. Although I have to write these two solutions, complementary solution and particular integral solution, and then make linear combination, as this complementary solution is a transient solution and it exists so far as or until the damping force exists in the medium. And you know, once our external periodic force acts strongly on the oscillator, this damping force starts vanishing. That means this damping force will become zero, and when the damping force vanishes, this solution also vanishes. So that's why it is a transient solution. I think if people get it well, so our final solution will be only particular integral solution, that means this much. That's all for today's class. I think you people must get all these things better. If you get all the things better, don't forget to like, share and subscribe our channel, so that this channel may be reached to all of your friends and they can get benefit of this learning. Thanks for watching. Thank you.